Hello, this is Mr. Sarisa, and today I want to talk about projectile motion, which basically is like throwing. So the example I'm going to give is throwing a ball. They also call it curvilinear motion, meaning that it's following a curve, but also it's going in line. So things that you need to know for whenever you're doing one of these projectile motion problems is that there's going to be something that's thrown up at a certain rate, and so that's a v sub 0. That's the velocity or the initial velocity of the object. Initial, I forgot to write that in there. And so that's v sub 0, and it's going at some angle here, and that's going to be how it starts at some angle. But if you know anything about throwing things, it's going to go up, or solid line goes up, and then it's going to come down. And at some point, it's going to hit the ground again. That's something that we're always looking for. And sometimes there's going to be some other initial height besides 0. So we'll have h as some initial height. And so through physics, and I'm sure some of you have seen similar equations to this, they come up with a couple of equations for the parametric equations. One is for the horizontal motion, and that will be x. And so very similar to what we showed before, if we made a right triangle out of this, that would be like our r cosine theta, except for this time it's v sub 0 cosine theta. And we multiply that times t. And so the t, of course, is time that after throwing it. And so that keeps going on all the way till it hits the ground, typically is when we stop that. And that will be our interval for t. The other one is the vertical motion. And so the vertical motion is affected by y, but it's also affected by gravity. So we have negative 1/2 g, which is the force due to gravity, the acceleration due to gravity. And that's multiplied by t squared. And then we also have, now this is the height that we're used to, the r sine theta, except for it's v sub 0 sine theta, and then multiply that times t, and then plus whatever the initial height is. So sometimes it's really nice, the initial height is 0, and we don't have to write that in there. But that's not going to be the case here. We're going to do something that starts at a height of 5 feet. So we're going to have somebody throw the ball. So who knows how tall they are, but they're throwing this ball starting at 5 feet. So you have to remember where this where the object is thrown initially. And so that ball gets thrown, and it still has to go down, and then so we'll have the ground like there. This person's starting it at a 40-degree angle, and with an initial velocity of 50 feet per second. Okay, so this could all be written into a word problem, and it probably will be. Instead of a diagram, you'll have to do the diagram yourself. But that's essentially what it looks like when you start it up. Oops, feet. And so we're going to answer a few questions, and these are all typical questions that you would see. So, for example, the first one is, well, find the equations. Even if they don't ask you to do that, you should do that anyway, because it helps you solve the problems. So, just following our guide above, we're going to set our x equal to 50, our initial velocity, cosine 40 degrees, so remember your calculator should be in degrees, and then times t. And then our y vector, the vertical motion, is described by negative 16t squared. Oops, I forgot to mention that too. G is always going to be, G will always be negative 32. Okay, or 32 rather. 32 feet per second squared. And so in physics you probably do 9.8 meters per second squared. But unfortunately the pre-calc book never does this. I like the 9.8 meters per second squared as well, but In the book, it's always going to do 32 feet per second squared. So if I multiply that times negative 1/2, I'll get negative 16 every time. So let's finish this up. Plus 50, the initial velocity, sine 40 degrees, and that's going to be multiplied times t. And then finally, the initial height is 5. So we'll add 5 to that. Alright, and then so we found the equations. Next question is, how long is it in the air? So how long is the ball in the air? And that's easy to solve because that means our height ends up being 0 when it's not in the air. And so we need to set y equal to 0, which means all of this, negative 16t squared, etc., will equal 0. And then it's nothing that we can really factor well, so we're not going to try to factor that. What we're going to do is just use the quadratic equation in order to solve that. So I'm sure you know the quadratic equation, or you better know it, the negative b plus or minus square root of b squared minus 4ac over 2a. And then solve for t. And when I do that, I get t is approximately 2.15. And so you might have done this on your own and been slightly different than I do. But one thing I would suggest in solving this, so you don't have to worry about rounding, I always use my alpha characters, A, B, and I'm going to use X here, or if you want to use T, actually, that might be a better one. And I use the store key. So I'm going to stow it into those letters. And so basically what I do is I did 50 cosine 40, and I stowed that into A. And then I took 50 sine 40, and I stowed that into B. And then finally, when I did the quadratic formula, I just stowed that into T. So when I got the answer down here, for T equaling 2.15 seconds, I stowed that into T, the T in case I needed it again, which I do eventually. So that came in handy. Alright, so how long is the ball in the air? And then for C, I looked for the max height. So if you're finding the max height, pretty much ever, you're using the x equals negative b over 2a. Except for in this case, x is really t for time. And then I worked that out, and it came to approximately 1.00. And if you wanted to store that, you could store that as well somewhere, and maybe an x, whatever makes it easier for you. And then a follow-up question to that is, or the t, that's the how long did it take to get there. So the max height is actually from your y. So you use the y equation into this. And you plug 1 in all the way through. And when you figure that out, plus 5, you work that out. And this time you get 21.1. And then another question is, how far did the ball travel? And this goes with that time equaling of it being in the air. And so this is where we'll end up using that t that we had from earlier. So we want to know how far it traveled, and that we're using the x, because horizontally is how you measure how far it traveled, not the whole curve. So we just have the 50 cosine 40, and then we plug our time that it spent in the air, so 2.15-ish, and we get 38.3 feet. And then, oh, I forgot to put feet up here too. And then finally, they want you to graph this. And so the graphing's pretty easy. It's what we did before, but it helps now that we can set our window to be between 0 and 2.15 because that's how much time it's spent in the air, and then just do zoom fit, and that will give you a really nice looking graph. Oh, one other part, the little hints to add on to this that I forgot to tell you is that when you're actually using this, the y equals or the x equals, you can still go into the vars on your calculator, and so it's slightly different though. You can still go to vars and then y vars, but you'll see the second one is the parametric equations. So you'll use the parametric equations and choose whichever one, x1 or y1, that fits your needs. And so if you use that and then remember to put your input into parentheses so that it comes out right, this works out really well, pretty quickly, easily, and again, you don't have to worry about rounding. Okay, I realize this was a long one, but I covered a lot of good material. I hope that it helps. Thank you very much.